I've mentioned that to solve our problem we're going to need one more constraint. So let's get that constraint now, and then we can make a start on our solution. The constraint is essentially conservation of mass, and I'm going to frame this as the conservation of flux along the channel. And to do this I'm going to introduce flux. Flux is effectively a rate of transport. Volume flux, which is the rate of transport of volume, has units of meters cubed per second, and in a simple flow like this channel flow, it's simply the velocity times the height, eta, times the width of the channel, which I'll just call W. More generally, we define volume flux as the integral of the velocity over a particular area. So when we define flux, we need to know the area across which this transport is occurring. For this particular case here, what I'm going to do is I'll consider a one-dimensional fluid element of unspecified size. And this fluid element has volume, V, which I'm going to write as simply eta times W times delta X, which is the length of the fluid element. I'm also going to assume that the flow is incompressible, and what that means is that if there's a certain amount of flux in and a certain amount of flux out, then the volume has to change by a certain amount. I'll write this as the change in volume equals flux in minus flux out times delta time, and you can see that that's dimensionally consistent. In other words, delta eta times the width divided by delta t for the change in time is equal to the flux in, let's call that U1 eta 1 times W, minus the flux out, let's call that U2 eta 2 W, and we're going to bring our delta x across to the right hand side. Now if we take the limit of delta t going to 0, and we also allow our fluid element to shrink in size to 0, when we can do this because we know that we're working in a continuum, then this equation simply becomes a differential equation, d eta dt plus d dx of u times eta is equal to 0. So we now have two equations for two unknowns, and we can begin to make some progress. The first equation is the equation of motion, and the second equation is our conservation of mass. You'll see that both of these have time-dependent parts, but armed with our knowledge of what this flow looks like, we're going to assume a steady flow, which means that du dt and d eta dt are effectively 0. I'll rewrite the equation of motion as u du dx plus g d eta dx plus g d h dx equals 0, and I'll expand out the derivative in the conservation of mass equation to give me a du dx plus u1 eta d eta dx is equal to 0. Then I'll substitute in for du dx, rearrange terms a little bit, and I'll get a u squared on g eta minus 1 times d eta dx on the left hand side, and I'll pull the dh dx over to the right hand side. Now you might recognize this u squared on g eta term on the left hand side here. This is just the square of the Froude number, so let's rewrite this equation again as the square of the Froude number minus 1 times d eta dx is equal to dh dx. So what's going on here? Well, we don't quite have a solution yet, but in fact this allows us to make some pretty good predictions about the solution. The first is that dh dx on the right hand side is known, and we particularly know that it's 0 at the top of our bump. Okay, that means on the left hand side at the top of the bump either d eta dx needs to be 0, in other words the flow needs to be flat, and in that case it turns out the layer height is symmetric across either side of the bump. But that's not the solution we found in our laboratory experiments. In that case, d eta dx was definitely non-zero at the top of the bump, and that means that the only solution we can have is one where the Froude number is 1, or u equals the square root of g eta, exactly at the top of the bump, and that's the solution I'm showing here in this blue line. So how do we understand the physics of this nonlinear flow? Well, the key point is that waves in fluids is really how the fluid communicates with itself. It's the way messages get sent around from one part of the fluid to another. For example, my surface height is low here, send some more water here to bump me up. As soon as you reach a point of hydraulic control, the waves can only travel in one dimension. In other words, the fluid can't really see what it's flowing into. It doesn't know that the fluid height is low on the other side of the bump. It just gets over there as quick as it can. And as quick as it can turns out to be the square root of g eta, or the phase speed of the waves. This leads to definitions of super and subcritical flow. So subcritical flow is when the velocity is smaller than the wave speed, and this is what's happening upstream. Downstream, flow is supercritical. Velocity is exceeding the square root of g eta. That means all the waves have to be travelling with the fluid, and nothing can travel back up the slope here. Exactly at the top, we have an exactly critical flow. It's called a point of hydraulic control, and that's where u exactly equals the square root of g eta. So you may not realise it, but you actually use hydraulic control in everyday life. The greatest example of this is every time you pour water out of a jug, what you're actually doing is you're regulating the height of the water that's flowing out. You know intuitively, although you may not have known the mathematics of it until now, you know intuitively that the water that is coming out of that jug is going at exactly the speed of the square root of g eta, where eta is the thickness of that flowing layer, and so you can automatically use the height to regulate how fast water comes out of the jug. Another example, you maybe this is less common life, but there were some experiments done a little while ago using the shallow water analog for Hawking radiation, which is the radiation that escapes from a black hole. Now, a black hole is sort of similar to a point of hydraulic control in that light waves can't get out of the hole. And this experiment effectively used a classical analog for Hawking radiation to understand it using hydraulic control. So the last example I want to give you is one you're also aware of, and that is a shock wave. A shock wave occurs when you get a transition from supersonic flow speeds, that is flow speed going greater than the speed of sound rather than the speed of shallow water waves. And you can get a shock wave, for example, travelling on the front of a plane when the plane exceeds the speed of sound. And when you do that, you all know you get a sonic boom, and a sonic boom is pretty much the equivalent of the hydraulic jump that we saw in our flow.